My name is Kevin, I'm supervised by Rui, and in this project we try to understand how the brain, in particular the neocortex, learn in a self-supervised way. So first I tell you about what neocortex is and what we mean by canonical microcircuits. I go through some of the theories that explain what is the computation in this microcircuit. Then I go through some of the evidence that show that the brain might use something similar to self-supervised learning. And I go through the experimental study on mice that we try to explain without theory. I go through the theory result, and then I end with conclusion and the future works, and some limitation, obviously. So the neocortex is just 2 to 4 millimeter, and it's 75% of your brain, and it's basically responsible for all the cognitive tasks that you do, language learning, literally everything. And if you look at it on the microscope, you could kind of divide it into 6 different layers based on the morphology and the type of the cells and the connectivity. But neuroanatomical studies show that the connectivity between these layers, it's in a way that you can divide them into columns. In fact, if you look at the mice barrier cortex, you could actually see columns and they're kind of separated. And each of these columns receive information from whiskers, and each of this column is associated with one whisker. So another interesting thing about neocortex is that this kind of structure is kind of similar across the species. And if you look at different areas of the brain, you can see pretty much the same thing, but we, of course, we're a little bit different in their connectivity. So in a canonical view, you can divide it into three different main layers. So thalamus, you can think of it, it's not a layer, but you can think of it as a router of information. So information goes to layer 4, after layer 4 goes to layer T3, and after layer T3 goes to layer 5 or 6, and then it goes out to other part of the brain. However, it turns out it's more complicated than that. So everything is kind of interconnected. Layer T3 receiving actually information from other part of the brain, for layer 1. And layer 5 is actually 2 layers, 2 sub-layers with different spiking patterns. Layer 6 is projecting back to the thalamus and is playing a role in attention, which makes it really actually difficult to understand what's actually going on within these circuits. So one of the theory, it's by Jeff Hawkins, and it's basically saying that your brain is organized into thousands of these columns, and each column processes information independently. So if you're touching a coffee cup, the information from your fingertip go through one column, and then other thing go to other column. But this column independently processes information. The first column says is a coffee cup, the second say is a coffee cup, the third one says no, it's actually a bottle, and then there's a water mechanism. So limitation with this is that it's absolutely non-hierarchical, but we know that the brain processes information in a hierarchical manner, in a sense that some lower level feature is processed by a lower area of the brain, and then the higher area is processing more abstract representation. And it's not scalable into all sort of data types, and it's not compatible with supervised and reinforcement learning because this framework is completely unsupervised. The other theory, which is more of a framework, I would say, is trying to explain how predictive coding, which was proposed by Rao and Ballard in 1991, can be implemented in this kind of different layers of a cortical column. So in predictive coding, basically the higher level, the higher area try to predict the activation of the lower level, and then what is unpredicted, or the residual or the error signal is kind of feed forwarded back to the higher area. So in this framework, they're saying layer T3 is encoding the error. So, for example, if there's some neuron in layer T3 that they fire when there's a negative error, and there are some population of neuron that fire when there's a positive error. And the deep layer of layer 5 is actually doing this prediction from higher level, the high area to low area. However, I mean, the neurocomputational mechanism for predictive coding in the brain is still in debate. We don't really know how this is kind of implemented, and what are these error signals and how they are kind of encoded with neuropopulation. The other theory, which to me is more compelling, was proposed and kind of revised by Rayleigh recently, and it's basically saying that the thalamus is playing a role. So thalamus is not just a relay of information. So in this theory says that the layer 6 is trying to send prediction into the thalamus, and then layer 5 and layer 2-3 jointly try to provide thalamus with the actual outcome. So you predict what's going to happen by layer 6, and then layer 5 kind of provided with actual outcomes, and then you get this kind of prediction error. However, there is no, experimental studies show that this layer 6 projection into thalamus are not driving, so it's not likely that they can make prediction, but it's still on debate. And there is some lack of experimental study on how this temporal prediction error is actually computed. Okay, so the recent study, more computational study, show that if you train, neural network basically, with a self-supervised way, then those neural network can have a better neural prediction of the neuron in your brain better than the supervised counterparts. And there are two similar studies. So they basically have different streams of neural network. They train it in a kind of contrastive learning. And then they realize that, each of these networks is kind of resembling one area of the visual cortex. So, these are recent study with, neuroscience is still doing more study to understand what is the learning algorithm in the brain. But these are some evidence that show that something like self-supervised learning could happen in the brain. Okay, so in our study, we're trying to explain this data. So this data was collected by Jordan and Keller. And in their experiments, they have more than one mouse, but the mice can freely run on this styrofoam, and they're wearing the visual reality glass, and the visual flow moves. So there is grating, sliding grating, and the speed of the sliding kind of coupled with the speed of mice. So if mice goes faster, then the slide it goes faster. And while the mice doing this, they're recording from the neuron in layer 2-3 and layer 5. And you can see the summary plots here for layer 2-3 neurons, which the x-axis is the time. So this is where the mismatch happened. So basically, while the mice is running, they just hold the visual flow. So basically, they violate the model of the mouse. So when they hold the visual flow, we can see that majority of layer 2-3 neurons, they are depolarizing in a sense that the membrane potential increases. Basically, they're more likely to fire. And that is quite reversed in layer 5. So layer 5 neuron, become more hyperpolarizing. So their memory potential decreases. Okay, so our theory says that layer 2-3 and layer 5 is jointly implement a form of autoregressive model. In a sense, the layer 2-3 predict what's going to happen, and then layer 5 provide with the outcome, and then we see the error. So you can formalize it mathematically using an energy function. So with this energy function, you can write, you could say that layer 5 is trying to minimize this energy function. The first term is sort of the activity of the neuron in layer 5 should match with the projection that comes from layer 2-3 to layer 5, and the second term is a nudging term which kind of forced the layer 5 neurons to encode the current input. From this, you can get the neural dynamic for layer 5 neurons, and then if you take derivative of this energy function with respect to parameter of layer 5, this WL5, then you can get the update rule parameter. You can extend this, you can add the part which is related to layer 2-3 here. So this term is basically saying the activity of the neuron in layer 2-3 should be equal to the prediction. So layer 2-3 parameters try to predict what's gonna be next. Similarly, you can get the neural dynamic for layer 2-3, and also if you take the derivative with respect to layer 2-3, the parameter of layer 2-3, you can get the update rule for your model. And one possible architecture, it's not the only one possible architecture that can capture an energy model is this architecture I'm showing you here. So you have a neural network that receive input at time step t and encode it, or we call encoding the phi xt, and then this phi xt goes through layer 2-3. Layer 2-3 try to predict what is going to be the embedding of the next, the input in the next time step, xt plus 1. At the same time, layer 5 receives a sparse input. The reason that we're passing a sparse input because there are evidence that
5 minutes.
Thank you. There are evidence that layer 5 is receiving a sparse projection from thalamus, because we know that layer 4 is receiving most of the projection from thalamus, but in layer 5 is receiving very sparse input. You can actually think of this sparse as a kind of augmentation, data augmentation, if you're familiar with within the self-supervised learning and computer vision. So layer 5 received the input at times that t+1 encoded, and then you do have a loss function here. So this loss function is sort of the prediction error. Then you do have another reconstruction loss here. So this is basically the second term is in our energy function. And you can, because you have some information about the action, because they're kind of coupled together. So you should be able to predict what's going to be the next action. You can replace this with any reinforcement learning, basically. So, you can just pass it or, try to predict what's going to be the optimal action that's going to be taken. For our simulation, we basically use synthetic data. So our data is 128 dimension, which is generated by 8 latent states, as is missing there. And each of the latent states is kind of changes with the speed. So if you increase the speed, the value of the latest state is going to increase, which in result, the value of the input will increase. And we train it by minimizing this loss function here. And then during the inference, what we do, we hold the visual flow. So visual input, which means that it's going to be 0. And then we record the gradient with respect to the unit. You can think of them as a neuron, and then weights, you can think of them as a synapses in your brain. And if you do that, you can actually capture. So if you look at the gradients of the parameters in layer 2, 3, the majority of them are kind of depolarizing. And then you could see that, in layer 5, most of them are hyperpolarizing. So yeah, what we did in this study, we tried to sort of propose a theory that the kind of computation in the cortical column can be modeled as an autoregressive model, and if you do that, we could capture the experimental data by Jordan and Keller, but of course there are limitations. So when it comes to neuroscience, there's always limitation here. So one of the important limitations is the oversimplified artificial neural network that we're using, but we know the biological neural network are more complicated. For example, in the brain, neurons are either excitatory or inhibitory, but in neural network, basically one neuron could inhibit one other neuron and can excite the other neuron. And we're going to add more dendritic compartments. So basically, you have a neuron, we have some dendrite receiving information from other area. Also, it's not quite clear how the lag is implemented in the brain. So if you remember here, I'm passing xt+1 and here xt. But you receive input at the same time, so how this lag is kind of implemented in the brain. We do have some sort of idea, but we need to investigate it rigorously. But we think that maybe the inhibitory circuits within this cortical column can implement that, and also you can get this lag of processing from layer 4 to layer 3, which could explain this kind of lag. The other thing is that we only explain the visual motor task. So mice was running, so it was kind of motor cortex and visual cortex. But another recent study by Colin, they're doing the same recording in layer 2, 3, and layer 5, but mice are just looking passively at visual input. And of course, we would love to extend our theory and see if we can explain data as well. Yeah, almost done. And the other thing, the task was very simple, obviously. So we need to try more realistic task. Maybe robotic control. We didn't get time to actually do it, but everything is kind of set up. So hopefully in the future we would have resolved for more complicated tasks as well. I'm going to leave you the references here, and if there is any question, I'm happy to take.
Okay, thank you. Yes.
So if I understand correctly, you said there's evidence. And the same supervised learning is a better framework to describe how the network works compared to supervised learning.
Well, okay, so if you mean this is slides, yeah?
Yeah, yeah.
Okay, so basically, it's flacking. So yeah, I mean, neuroscience has been like trying to understand what's the best, better architecture for visual cortex, right? I mean, they started with AlexNet, and they were just trying different learning algorithm as well. And it turns out that, I mean, this study was actually so surprising to me that if you just have two AlexNets here, so one here, and you just pass it like a video frame and train it with a contrastive predictive coding, then one of them gonna resemble the ventral stream, which is responsible for what is it that you're looking, and the other one would resemble the neural activation of dorsal stream, which is like where the thing is. So they train this, and then they compare the sort of neural activation of this pathway and this pathway, and they realize that when they train it in a self-supervised way, they get better neural prediction accuracy. And yeah, I mean, this is a study, I mean, pretty similar, but they tried it with shallow networks, but more streamed. So these are just evidence that self-supervised learning trained model is just better, not the best. And they're not claiming that self-supervised learning is the algorithm that the brain is using. It's just try to understand which one fits better. Yeah.
AlexNet is dense, so do you think with the sparse network might even?
Oh well, so AlexNet is a dense network. So he's wondering because he's wondering if a sparse coding or a sparse network would work better. Yes, we know. I mean, I assume so because the brain is kind of sparse, right? But because we're interested in the state of this network after training, I think maybe that's not the case. But I don't know any study that they tried that. But I guess it's really hard to train those sparse network because I mean all of the optimization algorithm for these are based on this kind of dense vector representation. But that was a good question.
Okay. Any more questions? Yes, Alpha.
So you were trying to explain the experimental data collected by Jordan and Keller, and you mentioned in your future work that you may want to try and go on to other tasks. So is there other experimental data out there that you may want to try that you may want to try next, or do you have any ideas of the kind of task? Yeah.
So the other study that we are really interested is that the mouse is just looking at some sequence of frames, and then there's a violation of the sequence. So if they expect A, B, C, D, or they train on to predict A, B, C, D, then they replace C with some random frame, and then they record the neural activity. So it's interesting because some of that result is kind of opposing the result that you see in Jordan and Keller, but it's neuroscience and different imaging techniques. So they're using calcium imaging, here they're using whole set recording. However, when they tried on the visual flow task, they get the same result. So we think that it's because the visual flow, it's more simple and the computation can be done within just lower area. But the other tasks, you kind of need memory, and you kind of need higher engagement of higher area in the brain. And there are another special thing about visual flow that is the first thing that basically you learn. So while you haven't opened your eyes, there are evidence that shows that visual flow is the first thing that your visual cortex tries to learn. Yeah.
And second part,
So very briefly, because
would you then extend your models for that?
Yeah, absolutely. Yeah. I mean, if that's the correct theory, you should explain both. So for sure.